For this year?
No, anything.
For this year?
For this one, yes. Sam?
I'm alright with that.
That is recording, so now.
Passing gift with them.
As a responsible student, I do not want that. Can you see the wink on the camera?
I think what they would. I think what they would do is they would just cancel the exam if they learned about it.
And then would we all then get to pass?
I don't know. No, you'd have to take the resit.
Or
Like there are 2 resits
It's not
now.
our fault that stuff got leaked.
Or
Surely we
instead
don't.
of doing that, we do revision, and when a question comes up that's similar,
Typical the old week.
galore, we'll just be like, so this we really need to focus on today.
Or
Yeah.
I'm going to expand slightly on what Sarah said by saying nothing of the same, a completely different idea. Burn the university down, we all get first.
I've already
Sure,
indicated.
not true.
I already indicated something last week.
What, that you're going to burn the uni?
There were like 3 people in the audience, so. It was,
Oh, I was there. Actually.
yeah.
We'll rewatch the
What
Last week.
is it? Okay, so what are we doing? So we have a group and we have a set X, right? And what that we got stuck.
Oh my, how do you do that with your hand? It's like the sliding tongue trick, it's genius.
Feel it out.
I'm in a giddy mood, I'm right now. Good music. Ooh. Like the reverse
Look
bounce.
at the other side of it.
Oh, we've not seen that one before.
There's only like 2 wires.
Yeah.
Anyway, so it's not
As far as working parts.
Is it all the one in this room that goes wrong? Is it all of them really?
Yeah.
This one, that's the
Yeah, but it's not the only one.
Oh, yeah, did JB's.
It wasn't that. The computer wouldn't. Oh no, it was that. Yeah, the overhead wouldn't go. We called IT after we messed with it.
Did they offer the suggestion of off and on it?
They did over the phone. She was like, "Yeah, we've done that."
Obviously. It's 29.
And then she came up. She came up and she was like, did the exact same things we'd just done, and then was like, "Yeah, it's done. It's broken. It don't work." We're like, "Thank you." And then we ran it over 2 doors
Oh,
after half an hour.
They are the band for one I remember dropped. I didn't need the bit off. You couldn't.
so like we have this today.
Can I have your notes? What's up?
Like there's this pub in Chester Street, they have football games on, so
Oh,
they
yeah.
have projectors. Do they have a visualizer there?
After a couple of pints, you start visualising. Not me, though. Yeah, I'll do all right.
All right, so we have a group. G acts on X. X is some set. Now what happens is you have some elements, okay? Like this. So what the identity does, it always keeps any element in place. Okay? There could be some other elements that keep this one in place. And then there are others that send it somewhere and send it somewhere else and send it somewhere else. And all these elements that you can send it to, that's called an orbit. That's what we said yesterday. Okay? And so this set X splits into orbits. They're equivalence classes, so it's a partition because so sometimes there could be just one element, sometimes there are just 2, yeah. Sometimes there are many. All that can happen. Okay, that's the situation we're in. Abstractly. Make sense? Should do if you remember what group action was from yesterday. Okay. So these are the equivalence classes of what we call tilde G, and I call orbits. And we had some examples, and there were more examples. 14.7, slightly artificial. So we looked at one where the general linear group acts on points in the space, 2 by 2 matrices in the plane. So there were 2 orbits, one has just a 0, the other one has everything else. Now, we'll do more examples of orbits in the tutorial, so I don't want to spend much more time on that. Now there is a definition which is 2 definitions in one. And starts like everything else, let G act on it. And then there are 2 things. So the first thing is when you have an element of the group and something that is X index little g, this is called the fixed point set of G. Okay, and the confusion starts only when I write the second one. So let X be in X, then G little x is a set of all G in G such that Gx equals X. It's called the stabilizer of X. Who's confused? I'm doing something wrong if nobody's confused.
Generally speaking, I'll do with this.
Okay, the definition is the same. One of them is you look at one element of G and then you go through all the points in X such that they are not moved by this specific 1G. The other one you start with a point there and you look at all the elements of the group that don't move it. 2 different things. Like in this picture, what second thing, this element would be is all the arrows that I drew here that go from the element to itself. And that's a stabilizer, that's the stabilizer. The fixed point set is just a fixed point set. There's example 14.9 in my notes say read it, but it doesn't shed much light. Do you want to see it? Oh yeah, it is important to remember that the big X little g is a subset of X, and the big G little x is a subset of G. Well, it's not so important. Okay, so you have some permutations of the set 1, 2, 3, 4, 5, 6. You look at what does the identity keep fixed? Well, everything. So fixed point set of the identity is the whole set X, because the identity, that's one of the conditions in the definition of an action, that the identity just maps everything to itself. And there's this one. So this permutation moves 3 to 5, 5 to 3, 4 to 6, and 6 to 4, but it keeps 1 and 2 in place. So 1 and 2 are fixed points. This permutation and that permutation, they move everything. 1 goes to 2, 2 goes to 1, 3 goes to 4, and so on. Everybody goes to somebody else, nobody stays put. So in fixed points, there are none. The fixed point set is the empty set. Okay? Now, when you look at the stabilizers, what do they do? G1. You want G1. What is G1? Well, all the permutations that don't move 1. So this one doesn't move 1, this one does, this one doesn't move 1, and this one does. So it's up and up. Okay. It's the same for 2. So this one doesn't move 2 anywhere. 2 goes to 2, 2 doesn't go to 2, 2 goes to 2, 2 doesn't go to 2, so it's this one on that one that's sitting the stabilizer of 2 as well. And for all the other ones, the stabilizer contains the identity. Okay with everyone? What's more important than to remember that xg is a subset of x is proposition 1410. Where's the dilemma? Let G act on X and X be an element of X. Then Gx, the stabilizer, is a subgroup. What do you need to prove that something is a subgroup? I don't think. Okay, so what does the identity send X to? Well, to X. So it's there. Yeah. Remember the definition says everything in the group that sends X to itself. X is the fixed one element that we picked specifically, no matter which one, but a specific one. Then the product, so G1x. If G1x is in there and G2x is in there, then G1, G2, what does it do on X? Well, by the second condition from the definition, it must do application by 2. If I first do the product in the groups, it's the same as if I first act by the second element and then by the first element. And if I act by the second element, I don't move anywhere, and if I act by the first element, I still don't move. Also in the stabilizer, how about inverses? Yeah, so if Gx because we had this kind of notes at the beginning, yeah? So now this x is that x, and this x is that. Do you want to think of it that way? Okay, so G inverse is also in the stabilizer, so that's it. Any questions? Yeah, this talks about the index of that subgroup in G, but it doesn't start let G act on X. It starts let G be a finite group. Acting on a finite set. And we pick an element from that set. Then the order of the stabilizer is equal to the size of the orbit of X. So sorry for Alicia now, she missed when I was giving the exam questions away.
Shame you didn't. Well,
Oh yeah, we have to learn everything. Okay, so what does this do? Like, you have this group G, and it has a subgroup GX, and then it has all the other cosets of GX. Right? So this index is the number of cosets. So the number of these things, which is 5, should be equal to the size of the orbit. Now, how does that work? Okay, so this is the set X. And somewhere there's the orbit of X. And then there are many other elements, and we don't care about them. Now, there is this element X. Okay? And the identity takes it to itself. And everything in the stabilizer takes it to itself as well. So if you have any other element of the stabilizer, by definition of the stabilizer, that's what keeps that point fixed. Okay? And there is some other point in the orbit, which is G1x. And this is what G1 takes X to. But not only G1, but also everything in this coset, that's exactly the element of the group that take X, this element in its orbit. And then you have another element in its orbit, so there has to be something that takes X there, and that is going to be G2, but also all the other things in this coset take X2, so on. Okay, so G3 will take X to this element, and G4 will take X to this element, but also everything in the coset will take X to that element. So that's the idea of why it's true. The proof, however, is, well, the proof is just the formalization of that idea. So we show that there is a bijection I between the set of all cosets of Gx and the orbit. What's the proof to in Yeah, I think the proof in the book is still incorrect. It was last year. So I'm actually trying to do phi that will go from the orbit to, I don't know where, G/Gx. And that's the set of all cosets. The factor group just seen as a set without any direction. So I want phi of any y to be the set of all g's in the group such that gx is y. Okay, this is what I said exactly. So this coset, I want to be all the elements of the group that map x to this element. So this is now what I've called y in the definition. Schismos. Okay, so first, is that even a coset? So does that definition even make sense? So we want to show that phi y equals ggx for any, if I take some g from there. So I look at anything that's what I want. I don't understand this anymore. Okay, so I want to show this. Yes. So when I look at anything that's the image of y under this thing that's going to be bijection, what does that mean? By the definition, it means that this g dash takes x to y, because that's what I said phi y was supposed to be. And then g inverse of y is g inverse of g dash to x, because that is y. I don't understand that proof. I don't understand my proof. So I forgot to study. Even I have to learn every week what I'm trying to do. Yeah, something wrong. Oh, okay. But also, G is in y, that's what we started with. So this y, on the other side, you can do G inverse Gx, which is x. So this is G minus 1. And this is just a dash. So x is equal to this. So G inverse G dashed is in Gx because it fixes x. So G inverse G dashed is in Ggx. But this is the identity, so this is just G dash. Okay. Yes, got there. So this means that phi of y is a subset of Ggx. Okay, I start with anything in phi y. In a messy way, kind of, I realized that anything also had to be in the coset. So the image of y under phi is a subset of the coset. Still need to, well, I'm trying to prove that they're equal, so I have one inclusion, I still need the other inclusion. So if I take, hope it's not called G dashed again in my notes, oh it is. So I take something that is in the coset. Now everybody's given up. I'm not giving up. Because it is in the coset, it means that it's in the form of G times something from the stabilizer, which I call G bar. It's still showing. No, it's not. There's something in the stabilizer. So what happens if I do G dash times X, or action? Okay, G dashed is G bar. What does G bar do to X? Well, nothing, because it's in the stabilizer. What does G do to X? Well, it sends it to Y. That was how we picked G. So if it's in the stabilizer, if it's in the coset of the stabilizer, then it's in the phi of Y. Okay, so also the coset is a subset of the stabilizer. It was much easier when I just drew a picture and said it's true than when I actually had to prove it. So that was first. Actually, the definition works. Okay, the definition makes sense when I say, oh, I look at, doesn't fit quite well. You have the definition. And second, I want to show that phi is a bijection. So that means that if I have a coset, I need to find something that is mapped onto this coset. Okay, so if Ggx is a coset, then Gx is an element which goes through this coset. So it's onto, and if It's also 1 to 1 now, and that's the end of the proof. Does it have any examples? It has an example which is called section 14.2. Okay, so the class equation is based on the following profound observation. So if you have this set X that G is acting on, and these are the orbits. So some orbits are small, they only have one element in them. Some orbits are maybe bigger. Let's say this is X1, this is X2, this is X3, this is X4, this is X5, this is X6, and all the other X's don't have a name. If you know the size of each of these orbits, and you work out the size of X. How? Add them all together. That's a very sophisticated idea, isn't it? So the size of X is equal to the size of all these 1, 2, what letters does it use in the book? N. Okay, so if this is n rather than just 6. So I look at the sizes of all these orbits, add them all together. This part of group theory one could do in primary school. Now, these orbits all put together for future use are just called X sub big G. So we had X sub little g, that was all the elements that are, this is all the elements. So X sub little g was all the elements of X that are fixed by a specific element of the group. So with big G, it's all the elements that are fixed by everything in the group. Okay, so X G is all the X in X. They are fixed by everything in the group. Okay? If they're fixed by everything in the group, then their orbit is exactly size 1, because nothing moves it anywhere. And if they're not fixed by something, then their orbit contains other elements because something moves them somewhere. Okay? And so this one can also be rewritten as the size of all these fixed points plus, and you only start adding from 4, which is called K in the book. So I goes from K to N. Where? This? That's G. I'm a robot. I'm not a robot. That's probably the main reason. If I was a printer or a plotter, it would never change. that are made of biological material, organic stuff. Okay. So that's the idea, which continues. Oh. Okay, so this you have for any action that you can think of. The class equation is an application of this to a specific action which we saw last day. It's called yesterday, no?
Last day.
Which was the action by conjugation. Do you remember it? So the action, when it gets G, which is from G, and X, which is from G as well, it sends them to G, X, G inverse. This is like similar matrices kind of thing. Did you do similar matrices? What did you do in linear algebra? Yeah, so what is a matrix? But it's only interesting, well, it's mostly interesting when it's like a linear mapping. Like we were talking about this yesterday when we were looking at 2x2 matrices and move lines to lines, and that's when it starts being interesting. So okay, let's do more of that in the tutorial. Not saying it's finished, I'm just saying that I'm going to do something else now. Then examples of what conjugation does. So okay, so for this action, this xg is called zg. And it happens to be a set of all x's in the group. Well, x is equal to g. That's not sigma, that's a g. Such that xg equals gx for all g in the group. Okay, it's the same definition as here. So just think that this gx, which was the result of the action, is now gxg inverse. So if gxg inverse equals x, that's the same thing as saying gx equals xg. When you do the action, you get what you started with. Okay? Not a problem. And this is called the center. Okay. Okay, so that's one thing. The second thing is an orbit. Snowing, the train's going to be late. Is a non. So an orbit which has more than one element is called the conjugacy class. Conjugacy And the stabilizer of So what was the stabilizer again? It's all the elements of the group that don't move X anywhere. Okay, so this is called the centralizer. Two colors, that's too much. So it's the centralizer of Xi, which is everything in the group that doesn't conjugate again. This is equivalent to saying that if you do G, Xi, G inverse, you don't move. So okay, so what was this equation again? This xg, this is now called the center of G in this particular action. And you have to add for all the remaining conjugacy classes the size of the orbit. But the size of the orbit is what did proposition, what did theorem 1411 say?
The order of an orbit is G colon GX.
But GX is now called C in this action. Okay, so we have an equation which says that the size of X is equal to the size of the order of the center plus the sum of the indices of all the remaining centralizers. The size of X. Okay, so what is the size of X? X was G. The fixed points form the center, and then the rest you need to add the indices of the centralizers of the remaining things, conjugacy classes. Okay. The proof has just been seen. Right? It's a reversal of procedure. First proof, then theorem. Good. Anything else that we need for now? Well, if not then. Well, if not then, see you on Thursday.